All right, so this should hopefully be recording. All right, video talking about forces, and this is like a beginning video, right? So it's nothing too crazy. Just going over like what a force is and a little bit of Newton's second law. All right, so when we say the word forces, wow, that's perfect. When we say the word forces, there we go, that's better. That's more forceful. Anyway, forces, I don't know, it's a word that you hear a lot, and in physics, physical science, whatever, we got to make sure we have the exact definition, or that is to say, a very good understanding of what it means, right? And you're probably going to tell me, well, that's obvious. There's a lot of misconceptions that get taught, and I don't really like that, so we're going to try our best to avoid that. A force is simply something that causes something else to accelerate. All right. So, like, if there's a car and you want the car to go, you need an engine. The engine is going to supply energy, of course, transferring maybe chemical energy, transforming it into mechanical energy. Right. That's what an engine is by definition. Like basically transforming energy into a usable form, usually chemical or electrical, into mechanical, right? So motion, okay? But when you think of a force, you're thinking of motion, but be very careful. It's not just something moving, something accelerating, okay? Something either getting faster or something getting slower, okay? You might say, well, how am I supposed to remember that? I mean, like, I don't know. You're just telling me that, and I don't know. It's a thing. Well, because the equation tells you it. It says that force is m times a, all right? And this equation tells you exactly what it does. It says, hey, a force, right? Wow, this is so pretty. A force, let's make this maybe a little bit bigger, is going to cause, right, some object with mass, right? The force will cause something with mass to accelerate. All right. I mean, that's really what you should think of when you think of a force. Okay, forces usually can be thought of as pushes or pulls. Okay, so when you think about a force, we can often think of a force as a push or pull. Okay, and this is good. This is a good way to picture it, because if I just say something accelerating, sometimes it's easy. If I take a baseball and I throw it, you can imagine that there has to be energy for my muscles to contract in order to cause my arm as a lever, right, to transfer some of that energy and put force into the ball, right? The ball, as I'm putting force into it, it's accelerating, accelerating, accelerating. When I let go, inertia continues it on its merry way. And that ball, if I throw it harder with more force, it'll accelerate more, which means it will get to a higher speed. Okay? If I do a little bit of force, I mean less acceleration. Okay? And, when you think of these forces as pushes or pulls, the idea is some of them are obvious, right? I am pushing the ball, right? If I'm playing tug of war, I am pulling the rope, right? That's easy. But if it's something like magnets pushing against each other, right, it's a little bit harder, because you're like, well, what's pulling? What's pushing? Well, it doesn't have to be physical contact, right? It could be magnetic forces that repel each other away or attract each other, right? But at the end of the day, it's a push or a pull, okay? I don't think there's really any exceptions to this. Not that I have a PhD in physics, but pretty good understanding of it. And yeah, a force is always gonna be one of these things. Okay, and if somebody comments and is at Harvard and says, actually, this force isn't like that, I don't know. I'd be curious to know. Let me know. But for freshman level physical science, this should hopefully be pretty clear. Okay. This equation, we need to make sure the right units. All right, so we'll just change colors here for a second. So force, we say F equals ma. We should know what m is, mass. And notice, by the way, m, just be careful, because this is like a symbol, right? It's a stand-in for mass, okay? If you saw a unit like this, that's 15 meters. So just be aware, you gotta, just because m is there doesn't mean it's meters, right? In this case, it's mass, so just be careful. Mass, though, is kind of annoying, because the unit we have to use, I shouldn't say have to, but the unit that it's default in, the unit that it's going to be in generally, is kilograms. Okay, not grams, kilograms. And I think it makes somewhat sense. Most things in your day-to-day life, when you measure them, their mass that is, would probably be in the kilogram range. Okay, so like this coffee cup, when empty, is probably, it's not a kilogram, but it's probably like half a kilogram, right? So I could say 0.5 kilograms, I could say a pound, I could say 500 grams, right? But like most things, right? You're working with a car, that's going to be kilograms. You're working with, objects in a machine that are made of metal. A lot of times kilograms. Right? It depends on what it is, but kilograms is reasonable. Okay, just be aware it's kilograms, not just grams. Okay, acceleration. Acceleration is a very specific unit or a very specific set of units. It is meters per second squared. All right, do not forget the squared. Don't forget it. Okay, this is acceleration. Okay, I'm going to put a little arrow up here because this is a vector. This is for a freshman physical science class, this video, so don't panic about it. It just means it has direction. Okay? You don't have to put the arrow. It's a good habit, especially if you take physics with me senior year, then I'll make you draw the arrows because they're kind of important. But for now, it's not the end of the world if you forget as a freshman. Good habit to get into to not. But where do we go with this? So meters per second squared times kilograms. Hey, it says right here F equals m times a. So force, ergo, is going to be kilograms times meters per second squared. That's a mouthful, right? I mean, this is the unit. It's not that it's wrong, but this is a lot to say, okay? And we decided, I don't know who decided this. It might have been Newton himself. I don't know. He allegedly was a very arrogant guy, so maybe he did name it after himself. I don't know. But we call this, this mouthful of units, we give it a better name, which is a Newton. Okay, N, capital N, spelled out. Oops, that's not how I'm going to spell that. Let's try that again. Newton. Named after Isaac Newton, the guy who gave us Newton's second law. What a guy. What a nice guy. Allegedly. Well, not really. Allegedly, he was kind of mean, but that's a whole other conversation. So newtons. It's a lot easier to say 1 Newton than it is to say 1 kilogram meters per second squared. Right? A lot easier. So we say newtons. Okay? So if you take all this, let's nuke this from orbit, shall we? If I take all this, by the way, if you want to write this down, you're like, wait, you can always pause and rewind, right? So don't panic. Let's do a practice problem. Let's say, you have a, I don't know, a 75 kilogram box is being pushed with 100 newtons of force. Find the acceleration. Okay, of the box, I should say, of the box. This problem, it's funny, I just made it, right? I already don't like it because I'm like, which direction? So let's add that. Being pushed with 100 newtons of force to the right. Okay, and that matters because, if you're going in a road trip and you want to go to New York City, right? We're in Iowa right now, or at least I'm in Iowa. If I want to go to New York, I should probably go east. If I get in the road and I go 75 miles per hour west, I'm not going to get to New York very soon, am I? Direction matters for a lot of things in physics, okay? Velocity is one of them. Acceleration is one of them. They're called vectors. Again, this is a freshman level class. You don't have to panic about that, but it's important that you think direction can matter. Yes? Like, I think it should be obvious, but if it's not, ask me. Put it in the comments. Why does it matter, right? But I think the analogy I just gave hopefully makes sense. So, continuing. How do we do this problem? Well, if I were you, first thing I would do is think, what equation do I need? Well, this is force. Probably Newton's second law is a reasonable guess, right? And then if I were you, I'd write out the units that I know and the ones I don't know. So, like, do I have a force? Hey, look at that, 100 newtons, right? Okay, 100 newtons. Yay. Do I have a mass? 75 kilograms. Okay, good. Again, you don't have to do this every time. It's just a way to strategize. On a problem like this, it's not that bad, but on harder problems, it can help you. You say acceleration. Hey, I'm trying to find the acceleration. So, okay, I don't know that, right? And then I'm going to, in this case, do some very basic algebra. So my force is 100 newtons. I'm going to plug that in. It's equal to 75 kilograms times A. Okay, in algebra, If I want to isolate something, that is to say get something by itself, right? I want to get this by itself. Right now it's being multiplied, okay? And it is essential that if you want to undo something, undo a function, you have to do the inverse function. You can't just pick, like, oh, I'm going to subtract it. Well, it's being multiplied. That's not going to do anything, okay? It'll do something, but not what you want, I should say. All right, so it's being multiplied. I better do the inverse function, the inverse operation, right? The inverse operation is division, right? Multiplication and division undo each other, okay? So in that case, I'm going to divide. I want to get this by itself, so I'm going to get rid of the 75 kilograms. How do I do it? Just divide by 75 kg. It goes bye-bye. In algebra, if I do it to one side, I must do it to the other side. So dividing by 75 kilograms. Okay, you might be asking, well, how do the units work here? It's newtons divided by kilograms. Remember that a newton is the same thing as this, kilograms times meters per second squared. So when you divide by the kilograms, guess what happens? The kilograms go bye-bye, and you're left with this, which, hey, that is acceleration. Look at that. Yeah, that's pretty nifty. So let's get a calculator. This is not too bad to do, but we might as well use a calculator. Why not, right? 100 divided by 75, and we get an answer of 1.33 repeating, okay? Which we can round to 1.33. I mean, again, this is not a quantitative analysis class, okay? So rounding to the hundreds place is fine. 1.33, okay? And the unit is, I'll change colors here, 1.33 meters per second squared, okay? And if you're saying to yourself, I don't really know what that means, like, what does it mean? Is that high? Is that low? Well, acceleration is every second how much faster something will get or slower. There's a third possibility, which is if it's changing direction, okay, which is still changing speed. It's still changing velocity, okay, because remember, velocity is what we call a vector. If you're changing direction, you're necessarily changing velocity. But yeah, for now, I mean, for these early questions, it's just, hey, I got an answer, 1.33 meters per second squared. Every second, this object would get faster by that amount, every single second. Okay, so after 1 second, it should be going 1.33 meters per second. After 2 seconds, it should be going, 2.66, and so on and so forth. Okay, which we'll talk about when we get to kinematics, which is coming up pretty soon. All right, so this is a beginning video, hopefully makes sense. Yeah, we'll go on to the next set of problems. Bye-bye.